about I'll start with talking about the discussion. So today's problem, Poisson distribution. We have sample of t equals 4 observations. Value of y is given and drawn from Poisson distribution. We need to remember Poisson distribution is invariant to time. So the function equals theta to the power yt exponential of minus theta in the numerator and divided by yt in the denominator. So first we need to derive the log likelihood function, the gradient and the Hessian. Then we have to derive the maximum likelihood estimator. We have to compute the maximum likelihood estimate theta hat, and then we have to compute the log likelihood estimate for each observations, the gradient and the Hessian as well, and we have to compute the total log likelihood estimate, parameter estimates, the gradient estimates and the Hessian. So first simply you need to estimate maximum likelihood, then gradient, then log likelihood, then gradient and Hessian. So let's go to, we're talking about Poisson distribution, so let's go to the basic Poisson distribution. But before that, a little bit of revision. Joint probability distributions. The motivating examples of the previous section focus on the distribution of y at time t, which is generally a function of its own lags and the current and lagged values of explanatory variable x. In the case where both y and x are stochastic, the joint probability distribution function, for example of t observation, as we can see, function of y1 to yt, then the x1 to xt, which are explanatory variables, and all of them for unknown psi, which is a vector of parameters. An important feature of the previous example is that y depends on the explanatory variable x. Both are time variant. To capture this conditioning, the joint probability distribution is expressed as y1 to yt, x1 to xt for all psi or all the parameters. Then we have split into conditional distribution and marginal distribution. Now in conditional distribution, y1 till yt is conditioned on the explanatory variable for all psi parameters, and in marginal distribution we are only concerned with the explanatory variables depending for all psi parameters. Psi can be decomposed into theta and theta x. In the second equation is just decomposing them to theta and theta x, where theta is for conditional distribution and for marginal distribution the parameters related to x, theta x. Another important concept, independent and identically distributed. Just to recall very quickly, independent and identically distributed, IID. The distribution of y does not depend on the lagged of yt minus 1 I, that is independently distributed. Then identical, distribution of y is same in each time t, so y is identically distributed yt. These two properties are jointly called independently and identically distributed, IID, independent and identically distributed. So y1 till yt is independent of the explanatory variables x1 to xt, and yt is IID with density function of yt theta. The conditional probability distribution function is the second part of the previous equation. The time invariant models such as count model is the example. If both y and x are independent and identically distributed, then y is dependent, yt is dependent on xt, so that becomes the conditional distribution. So previous one is the marginal distribution, now it's the conditional distribution. That's all. Dependent. If assuming that y1 to yt depends on its own lag but is independent of the explanatory variable, then the joint probability density function is expressed as a sequence of conditional distributions, but conditioning is based on lags of yt. So by standard rule of using the standard rule of probability, the observations are as follows: y1. So now we are thinking about only the conditional distribution. Then second one of y1, y2, so y3 condition upon y1, y3 condition upon y2, where y2 is the initial value of marginal probability density. Extending it up to t observations, the joint probability density function becomes, so we are just extracting the initialized value, and then it comes from, it starts from 2 t, the time that starts from 2 up until t, and yt is conditional upon these lag values for all theta parameters, but it is independent of x or the explanatory variables. So this is in case of when it is dependent. Good examples are autoregressive model and bilinear model and arch model. So the autoregressive model with heteroscedasticity, where we talked about y1 to yt conditional upon x1 to xt for all theta parameters. We're taking out the initialized value on the left, and then we are starting the process, the sequence from 2 up until t, where yt is depending on its lag value up until y1, xt and x is lag value. So yt is depending on its lag value up until y1, whereas x and xt and the lag value of xt up until x1, and so the sequence starts from 2 for all theta parameters. Autoregressive model, the joint probability density function for AR1 model, the conditional distribution where yt is conditioned upon its own lag yt minus 1 for all theta parameters, and this is simply, as we know, the autoregressive equation yt minus rho yt minus 1, so we have already discussed that. And we are just taking 1 minus rho squared down just at the bottom, because the variance is sigma square by 1 minus rho square. We just have to divide it everything by 1 minus rho square. So let's go to page 17. Just have a quick look through gradient. So first difference of gradient of log likelihood parameter LT theta with respect to k by 1 parameter vector. So if you have k columns, k rows in one column, k by 1 parameter vector theta, if our parameter vector of or the parameter estimates is k by 1, it will yield k by 1 gradient vector, which is also known as the score. So taking the first difference of log likelihood function LT theta, or log likelihood parameter, basically the maximum likelihood estimate, we simply have k by 1 gradient vector. So first term is the mean multiplied to the summation of all gradient parameters. So the individual gradients are summed up together. So the maximum likelihood estimator is obtained by setting the gradient equal to 0. So we can obtain the maximum likelihood estimator by setting the gradient equal to 0, as we can see, and then solving it for theta hat. So if for Poisson distribution, the gradient is, well, we take out the mean 1 by theta, because it's just the first difference of the log likelihood estimation log likelihood function of Poisson distribution, summation of yt minus 1. So log likelihood estimation of the Poisson distribution. Have a look. This is Poisson distribution. We take the log likelihood estimation, where it is taking out the mean, and then log of yt log theta minus log of y1 up until yt divided by t. So if there are three observations, as we can see, we take out the mean, which is 3, adding all them up, summation of yt log theta minus log over the sequence 8 3 4 divided by 3, and then we set that to 0 to solve, against 0 to solve the value of theta. Now let's go back to our page 17. There you go, yt minus 1, and because as you can remember, log theta, so we're doing differentiation, we remained with this term minus 1. Everything in the rest of the terms, integration becomes 1 or 0, so it equals 0, and we can solve it. So for the maximum likelihood estimator, just yields simple mean, the sample mean with the gradient. So theta hat, we have estimated the maximum likelihood estimator, sample mean, the sample mean. And what about Hessian? Hessian is when we differentiate the second time the log likelihood function. So we are differentiating again. Remember, for every k by 1 parameter vector, the input if is k by 1, that means just one column data. Hessian becomes a symmetric matrix, which is k by k, that the number of columns equal to the number of rows. So while gradient was, in case of k by 1, it remains k by 1. If it was k by 2, it would become k by 2. Now is different. In Hessian, we are concerned with the number of rows only, because it's a square matrix, and on the rows across the matrix, everything changes only in the denominator, where we have d theta 1, d theta 1, then d theta 1, d theta 2, up until d theta 1, d theta k. And by columns, we're going down by the column, we have d theta 1, d theta 1 divided by d theta 2, d theta 1. So the first term is changing now up until d theta k, d theta 1. Take the mean out, and summation of individual elements multiplied to the summation of individual elements of the Hessian. And the conditions of the for negative definiteness in Hessian is, the first value is negative, then the 2 by 2 becomes positive, 3 by 3 is negative. So all even are positive, and all odds are negative. If k equals 1, the condition is negative. K equals 2, the condition is first, then h1 on negative, h1 on the second. 2 by 2 becomes positive. Okay, so that is a very quick look into the problems. Let's go back to the programming part now. As we can very quickly see in basic Poisson code, the difference clear all and CLC for MATLAB remains same. For RStudio, clear all is replaced with remove object function rm, list equals is, where all is true, e under is, graphics is off. Then we need to load a compatibility requirement for R. Then let's focus on MATLAB now. First comes the input value 834. We make a row of input 834. Also we make in R is in R this is a concatenation C. Then comes T. t length of y equals length of y the time theta. In theta we include the mean, we already incorporate the mean, then log of t equals y, comes the log likelihood function, log of t equals y log theta minus log of factorial y, because as we can remember the log likelihood function had the factorial in the end. Then the gradient, which was y divided by theta minus 1, y divided by theta, because everything we're taking to our left now, y divided by theta minus 1, as we can see, y divided by theta minus 1 in gradient. Yeah, Poisson distribution, just have a look. We're taking this one, y divided by theta, y divided by theta, mean divided by theta minus, so just this one, the mean divided mean, and y divided by theta. So mean, then y divided mean of y is already theta. Theta already has the mean. Theta already has the mean in it, which is mean of y. Theta equals mean of y divided by theta. Y divided by theta. Mean is already included. Minus 1. In minus y divided by theta square is the Hessian. Display. Now when we're focusing on display, sum of y, where we're summing y, the mean of y is simply the theta. Log likelihood function is mean of the log likelihood function estimated earlier. Display is replaced with CAT in R. Let's see what CAT is. Concatenate and print. So just concatenate is C and CAT is concatenate and print. So first we are introducing that this is how we will put in the print command /n, then CAT, sum of y remains same within the inverted comma, then comma, then sum of y. Instead of doing number to string sum of y, just simply sum of y, then comma, then the /n thing that we introduced in the beginning of the sentence. That's all. The mean of y, theta /n, log likelihood, everything remains the way it is. Interestingly, in the second part, when we are displaying manually yt, log lt, gt, ht, what we're doing is we concatenate, not concatenate and print, just see concatenating yt all in double inverted commas, comma, log lt, log gradient, log Hessian. Then the important thing, interesting thing comes up, which is if you're talking about print. Interesting thing, there's a lot of things in print. First comes X, which is the matrix of we're printing the matrix of our concatenated values y, log lt, gt, ht. We're giving it a matrix structure. Then the dimension names equals list. Let me see. Okay, now comes the names. First the matrix, the dimension names is taken from the list of row names and column names. Already we have introduced row names and column names, number of rows up until t. This is a big equation. Just remember, first we are introducing the row names, which is we're creating row names, and in row names we have the sequence of t. So all the t observations. In column names we have because we are just putting everything in double inverted commas is string variable. We are creating a string of matrix, and we're inputting all of this into print, where we are in the first part of print command. We have the matrix command, matrix function. We're creating matrix by concatenating all these four estimates: YT, logality, gradient, and Hessian. Just see, and comma, the dimension names, dim names, equals list of the row names comma column names, where the row name and column name will be displayed, comma, number of rows in row equals up to t. And then comes graph generation. Now for graph generation we use a for loop, like in MATLAB. The theta values, the parameters are starting from 0.1 till 15. Log L is for storing, we're passing the zeros, which is equal to the length of theta for the first column, and then the sequence for I is equal to 1 to length of theta. We run the log likelihood function again and end it. So we're basically doing the maximum likelihood estimates here. In theta we are using sequence command. We're passing 0.1 to 15 for a gap of 0.01. This is the sequence. And zeros, now instead of passing zeros directly for as length of theta rows on first column, we pass array. Okay, now let's see what array is in R. Come on, array. Machine is too slow. Multi-way arrays. Array, there is no data. The first portion is reminder of data, so we don't have data. We're passing zeros. We're passing zeros. Data is 0. Then the length, the dimension equals the length of data. So if there is no name, let's not think about it. The dimension is here, the length of theta, which is the length of the data, which is theta, length of the data. And dimension name, if there is any dimension name, then it's there, otherwise it's not. It's automatically becomes 1 because there is just one column that ends with 1. Okay, just remember this for now. For I is equal to 1 to length theta, for I in sequence of theta. Okay, we have already explained the sequence of theta, already defined, we have already defined sequence of theta. So the sequence of theta, we have already developed theta, then the sequence of theta is, for all values of theta goes in I. Basically this would mean the length of theta. Sequence of theta, not extracting, remember sequence of theta is not extracting the values of theta, rather it's just extracting the length of theta. Then the log likelihood function of y log theta minus theta I log factorial. Now interesting thing, inside brackets, when the iterations is supposed to happen, we put third bracket for R, while is in MATLAB first bracket remains as it is, but third bracket for R only when we are putting I. Remember that. For the rest it's not the same. Then comes subplots. Subplots are quite easy in MATLAB. You just have to pass in the subplot command. That's all. In R we start with figure, which is also in, we start here Then layout, this is the important thing. Layout, be quick today. Layout, what is layout? Let's see. Layout is specifying complex plot arrangements. So we are actually passing that we want a column, a matrix of plots which will be 2. So we are concatenating because we want 2 plot matrix. We want 2 plot matrix. We want that by rows, and number of columns will be 2 as well. Number of columns is nothing that I input, it is simply the size of the matrix, because it's a 2 by 1 matrix, so the number of columns is 2. If you had a 3 by 1 matrix, and col equals 3, that's all. So it will happen by rows, the results will appear in rows, and we are concatenating basically matrix graphs. So after I pass in this command, I can simply create regular plots. I don't go for subplots like in in MATLAB. The added advantage is that in MATLAB automatically positions the matrix, where we're by passing this command in R, we are controlling the position. So plot theta, with plotting theta against the log likelihood function. So y label, we have the log likelihood function x, we have theta, and type is equal to line graph. L is line graph. Okay, color dark blue, main is the main title, log likelihood function. Y lab is the expression of the theta that is collected from theta. X lab, x is theta, y is log likelihood. Y x lab, y lab is expression of, I don't know what is expression. Paste log theta, I'm not sure, right? Histogram, custom bar graph, each histogram, very simple, absolute values of log likelihood theta. LWD is equal to 20. This might be some type of, okay, what is expression? Let's see. Unevaluated expressions. It is a vector type expression means argument. Okay. Grades or tests for objects of mode expression. Anyway, just remember, paste the log likelihood in ylab. So it is simply the title creation. Paste log likelihood and theta. It's difficult. ylab, you see, it's difficult. There must be manual ways to make it in R that we would do in MATLAB, I'm sure. So for now, just remember that we are plotting theta against, this is what I have to pass theta against. Log likelihood, type is the line function, color dark blue, that's all. Titles we can deal with. bty equals L. Paste. Let's have a look. Inverted commas, log up to t hat theta hat. Oh, I think we want the results here in graph. That MATLAB will not be able to produce, because we want these in expression where it will show that theta equals 3, and it will create up until log likelihood functions up until t. Big deal. expression is basically creating equations. Good job. Okay, so now the next problem, problem 3 is exponential distribution. Exponential distributions is basic exp. Let's open it first for here, then we'll go through things very quickly. Basic Poisson B exponential, basic exponential, this one too. I don't need basic Poisson anymore. Okay, let's just pause the video. Basic Poisson, let's just pause it. Pause the video for a while. Okay, now we have basic exponential, and let's see how things are now. Exponential distribution, we have t equals 4 observations where yt is equal to 5.5 to 3.55 is drawn from the exponential distribution. First we need to derive, as well as this is the exponential distribution, so just have a look into the exponential distribution. That's all, very simple. Poisson is done. Exponential for all y1 till yt, if they're IID from an exponential distribution, then the function is theta. Exponential of minus theta multiplied to yt for all theta values that are greater than 0. The log likelihood function is just simply taking the log of it, which is mean first term summation of log theta minus theta yt, because exponential of minus theta yt, so first term is log theta, then minus theta yt, it will be separated. So basically we are taking out log theta, log of theta minus theta, because this is invariant yt, 1 by t, just mean of yt, log theta minus theta multiplied to mean of yt. That's all, very simple. And so the gradient and Hessian would be what? Hessian for exponential is log theta minus, okay, just start with gradient. One by theta, gradient first difference, because it was log theta minus theta multiplied to mean of yt. Log theta becomes 1 by theta minus mean of yt is the gradient. Simply you can solve it taking it on the left hand side, because it is equal to 0. So first just take both them in both parts, split them up, and then just fix them. Theta equals, now y goes to denominator, that's all. The mean of y goes to denominator. Theta equals the mean of y. Inverts, that's all for exponential. And for Hessian, it's not a lot of different. It is just minus 1 by theta square, we don't have y, and minus 1 by theta square is less than 0, so it's negative for any theta. The condition in equation is satisfied and its maximum is achieved. Maximum has been, which is negative, so If we put in the Hessian instead of theta, if we put in the value we have estimated with gradient, we have got a negative value. And because this is negativeness, the sign confirms negative, positive, negative for any theta, because this is just one term, theta square. Negative, positive, negative, value is negative. Hessian at each observation, evaluated maximum likelihood estimate is constant. Each observation evaluated at the maximum likelihood estimator is constant. Table 1.2 shows that. Okay, let's look for table 1.2. Table 1.2 is constant. For each observation, Hessian is constant, which is negative, confirms is negative definiteness. Okay, good job. Now let's just see how the maths are done. First, again, clear all CLC, where we do RM least equals in bracket least equals is least equals ls in bracket all equals true. Graphics is off. Then we put inputs where y equals as a row. Load the package and create a matrix by concatenating. See, t equals length of y as before, theta, as you know, 1 by mean y, log of theta. Log likelihood function is simply log of theta minus 1 theta divided by y, log of theta minus theta divided by y. Sorry, log of theta minus theta multiplied to the mean of y, which is we have passed in 1 by mean of y in theta already. So where theta equals 1 by mean of y, because from gradient theta equals 1 by mean of y. That information is included when you are first time putting theta in. 1 by mean of y goes in, multiplied to y. Second, first is putting the value of theta. First step is putting the value of theta estimated with gradient, then defining the equation. Theta multiplied to y. Gradient is 1 by theta minus y, because theta equals 1 by y. So taking everything on the left, right side is 0. Gradient is 1 by theta minus y, 1 minus 1 by theta square for Hessian. As we know, everything else is same. Instead of number of string, we just pass all along number to string function, just pass along this. In concatenate CAT and print function. Then again, row names is a sequence, column names is the matrix concatenated matrix of our output estimates ones. Now first we made zeros, now we're making ones, where again in ones we're passing on the array function where the values will be 1 for t rows and 1 column, for t rows and 1 column, kind of like that. CT1 matrix, our names, column names, that's all. Everything else remains same. For generating graph theta, we have the sequence and the log likelihood function is passed along, so that ln L values are estimated t log of theta minus theta sum of y, t log of theta minus theta sum of y. Let's go back to the here normal, not normal, log likelihood function. We just need to get the log likelihood function of exponential distribution, which is this. I'm sorry, t log of theta, t into multiply to log theta, theta into some y. Theta into some y, t multiplied to log theta. So basically just, you multiply both sides with t and then t turns to 0, so t multiplied to log theta. Log theta is t multiplied to, the other way to write this, t into log theta minus theta sum of y. Yeah, because we're just connecting them. Then comes, as we see it, C12 by row true. Number of columns is the total number of elements in the matrix. Type is line x y, the next by expression. So okay, third example would be Poisson exponential. Then comes normal distribution. There are two cases. First of is variance is known in this equation, y2 minus mu by 2 sigma square. If variance is unknown, the mean is known with a value of 2. Mean and variance both are unknown. Three cases actually. First, variance is known, then if variance is unknown, mean and variance both are unknown. What will happen then? So basic normal, like, let's see. Basic normal. What's the difference? I'm not sure. Let's see. I'll have a look. Now we are doing the normal distribution where there are 5 observations, values are given, and the normal distribution is y minus mu whole square divided by 2 sigma square, where the variance is known, theta mu is unknown. We need to find out the log likelihood function, the gradient, and the Hessian as before. Then the second case is when the variance and the mean, variance is unknown but mean is known. The third case is when both mean and variances are unknown. So let's just jump in here, where after exponential we had normal distribution, yt minus mu whole square divided by 2 sigma square. With unknown parameters mu and sigma square, if both are unknown, the log likelihood function becomes simply take the log likelihood of this. Mean is on the left and minus 1 by 2 log pi minus 1 by 2 log sigma square by 1 by 2 sigma square summation of yt minus mu whole square. That is very known to us. Just remember the line, that's all. 1 by 2 log plus 1 minus half sigma square t by t minus mu whole square. That's all. If in case when mean and sigma square both are unknown, basically now it will not be same as before. We need to estimate mean and sigma square both. Now comes the question of iteration. In case of t is equal to 6 observation, they have shown how that is done. Let's do it in MATLAB and R. Again, clear all. First we pass in our values. Wow, here the data is in column, not in rows, in columns, and so we use not C concatenate but C bind by column. Whenever you're creating a data, we in R by row is C is fine. By columns, I mean in columns, the values will come in columns. It'll be one C bind. Then log the y is fine. Again in theta we pass in the mean of y, display which is concatenate and print, MLE n slash MLE n. N is giving space and it's creating area for slash n is getting area for printing. Here's the space, then it must end with n always, then theta n is printed out. Define the log likelihood at each observation. Minus 5 log twice by minus 0.5 y minus theta square. Log of twice pi minus half log sigma square. Oh, we don't use sigma square here because we know here the variance. In this case we know sigma square, half y minus theta square, so we do it without sigma square. MLE for each observation, again n, start with n and end with n, fine, end with n. R names, row names is the sequence of t. It's not necessary here in MATLAB, but in R is necessary. In column names we put because it comes in table yt log t. Then print matrix first, the matrix which will include C and the matrix with y and log lt. And those dimension names will be list of row names and column names equals list of, and number of rows will be equal to t. So think about it, how you're constructing. First, what values will come in from that we have already calculated, yt and log of yt. Now the names of the values will come from dim names, where list will take the list of row names and column names, and number of rows will, the length of the number of rows will be equal to t. Oh my god, this is a bit complicated, I should say, to remember, difficult to remember. Evaluate gradient. Gradient is y minus theta. Let's have a look. It's all about the econometrics. You see, for normal distribution, gradient is mu equals y bar sigma square yt minus y bar, because we have two cases. First one is for mu 1 by sigma square t yt minus mu, and for this gradient is for mu, I mean normal distribution, log likelihood estimation, and for sigma square 1 by 2 square 1 by 2 sigma to the power 40 y minus mu whole square. Gradient first comes the mu 1 by sigma square t, second comes the variance, mean and the variance in the gradient vector. Sitting against 0, mu is y, sigma square is equal to yt minus mu whole square. So just see, here gradient is y minus mu. Gradient is y minus mu. It is very simple here. Gradient is simply y minus mean, or the y minus theta. Y minus mean is theta, so you take everything on the right hand side. So y minus theta. Y minus theta. We're going to log MLE for each parameter. G equals mu of mean of, so y minus theta, then we take the mean. Here in the equation they have directly done that, y bar minus mu hat. So first do that, then we take the mean. Gradient at MLE. This is for each observation. Okay, this is for each observation, and this is total maximum likelihood estimation, the big one, the big GT and the small GT. Starts with n. Again, same thing, same command. Tolerance. There's a tolerance here. Why am I using a tolerance here? No documentation. Tolerance. Okay, you are defining the tolerance here. Remember, if else so the gradient must be below the tolerance. I'm not sure this was not necessary, but yeah, just have a look. Hessian equals minus t. Let's have a look. Normal distributions, Hessian 1 by 2 sigma to the power 4. See, 1 by sigma square, because here sigma square we are not passing in sigma square, so just minus t. So just minus t. Fine. Hessian function. Now comes the iteration. Start with that. Look likelihood estimate, mean of y, then variance is mean of y minus mu whole square, y minus mu element by element squared. So taking the mean of that, simply taking the mean of that, very simple. Gradient and Hessian, have a look into gradient. Y minus mu. Okay, display butte generator of mu and sigma, passing the values for mu and sigma with sequence. Then we'll use for loop. This is interesting. For I, in sequence of number of rows, length of zeros, length of mu and length of sigma square. Mu's will go by rows, sigma square will go by columns. Okay, because I'm talking about Hessian here, I guess. K by K. Okay, so we have two parameters. In rows, length of mu, in columns, length of sigma square. We're defining it separately, and zeros will pass in for number of rows and columns. Here we're doing it directly in MATLAB, but in R we're doing it separately. So for I equal I in sequence number of rows or length of mu, same thing. And for j in sequence number of columns, in that case we are estimating both together. So basically, so here you see, if you have a specific number of rows and number of columns and you want the estimation to happen for all across number of rows and columns, you can do this. You create an array with zeros for fixing the size, half t log to sigma square summation y minus mu square divided by sigma square. So you see in some places log likelihood will have values from both I and j, because it will give me mu and sigma square, mu and sigma, both values. Basically mu and sigma square, because we have defined it sigma square. So first we have log sigma square j. You see, whenever sigma square is coming up, we're putting in j. Whenever mu is coming up, we're putting in I. Classic case of loops across columns, controlled columns and rows. Perbs. What is perbs? P-E-R-S-P. My god, so many things in R. Perspective plots. This function draws perspective plot of a surface over xy plane. Okay, so we're talking about a surface map. So it creates a surface over a plane, which is fine. Perspective plot, because we have three-dimensional inputs, right? Mesh grid. Okay, see, perspective plot and mesh grid. Edge color, where theta equals 45, 15, expand 0.5, 40.5, 15. These are just initialized values. Tick type detail, color blue mu 40 and 15. Edge color black. We don't need it for MATLAB, it will do it itself. but here we're passing the initialized value. Great. Okay, this is the second session. Here we are gonna look into some of the applications directly for whatever we learned up until now. The first problem is a model number of strikes. So we have data or the number of strikes per year YT in the United States from 1968 to 1976. The number of strikes is specified as an IID because it is the number of strikes are interestingly what should I say, the number of control alter I, I'm not sure, I think it will remain here. Okay, the number of strikes is a Poisson distribution because it is random, it happens randomly. So Poisson distribution with unknown parameter theta, we need to find the log likelihood function. We have to estimate maximum likelihood, estimate theta. We have already done these things. Use the estimate theta to plot the distribution to see what's the number of strikes, the Poisson distribution of number of strikes. So it is a model of the number of strikes and we have to do it in histogram. Let's do it. So as we can see, first again we are passing in the data that is given to us. Theta is mean of YT, we already know that. Where the mean value goes in, then we have just to concatenate and print theta and plot the estimated distribution. Plot is just plotting estimated distribution of strike numbers, how many strikes happen each year. Am I doing the right thing here? Yeah. So 0 to 20 years data, sequence 0 to number, maximum number of y with one interval. F is Poisson distribution of y and theta, y, x, y. So we are just talking about x and y and theta. D points, Poisson distribution is replaced with D points in our same thing. Start with figure 1. We're talking about a histogram bar of y and f, y and f. Type is line, color dark blue, then comes as well as mean. Y lab, just memorize it, man. The y title is expression of paste expression. Think about what we are expressing. We are expressing theta, y, and function of y and theta. So function of y and function of theta, both. Good. Function of y and theta. Theta is a value, rest is inverted commas, and then paste, then expression. Fine. And bty is the type, which is the line. Histogram, let's see what they have for histogram. It is very simple in MATLAB, just figure and bar, that's all. Figure, x-axis I, y-axis I, bar. What does that mean, bar? I'm not sure. Bar is set of query graphical parameters. No, read only, false. Okay. Passing them as tagged values. Okay, sure, no problem. Bar. Okay, x-axis I, y-axis I. Histogram starts with y. Here y. 11 breaks each year. I mean, this is the seasonal breaks. Basically, you're just giving it in breaks, that's all. Number of strikes, that's all. This is very simple. So this is the part we need to remember, which is par. Par is set of query graphical parameters. So in both cases, we're just mentioning that we want the x-axis will be up to I, the y-axis will be up to I. That's all. Okay, this problem is solved. As we can see, there's nothing very interesting. Medal of the duration of strikes. So there are 62 observations taken from the same source. The duration of strikes in US, the duration of strikes in US per year is in Y. Durations supposed to have an exponential distribution. Durations generally have an exponential distribution. So when that is having without I mean any time variant, so this is not time varying, this is just randomly happening. Poisson distribution, again we'll do that for all. So let's have a look into duration. I think that is very easy to load the data. All rows, column 1 located, just load the data as matrix. So basically we want the system to take our data as matrix. Oh sorry man, no, what I wanted to see is help as matrix. In our matrices creating, where as matrix attempts to turn its argument into a matrix. Is matrix just if argument is a matrix or not. So one is either it's a test or it is turning. So I'm just turning as matrix the strike number that is coming with my inputted data. I want the data into matrix. I'm converting the data, input data into matrix, that's all. But I'm just simply taking all rows in column 1, that's all. So theta is the mean, 0 to 300, y divided by theta multiplied exponential of minus y divided by theta. Coming from the equation, sequence is 0 to 300 in 10 intervals. Figure, plot and histogram. No new thing. Plot yf ylab function of y. First start the inverted comma, put f in starter bracket, put y, semicolon, finish the inverted comma for y. Then theta is a number, it shouldn't have any semicolon, comma, then semicolon for locations of theta in the bracket. Sorry, inverted comma ends in the bracket, another inverted comma ends in the bracket which was starting with f, and broad brackets, put them under paste function, and the paste function comes out after expression. Okay, what is paste function? Paste base concatenate strings. So this one actually concatenate strings, collapse null. One or more are objects to be converted to character vectors. So I'm converting them to character vectors. Or you must have a lot of examples as character. These are not very helpful compared to MATLAB. Help is much better. Anyway, acceptable because it's being developed by individual users. For XLab duration of strikes, everything remains same. No big chickiness here. Let's start with asset prices. Data consists of Australian, Singapore and Nasdaq stock market indexes for the period of 3rd January 1989 to 31st December 2009. A total of T is equal to 5,478 observations. Consider the following model of asset prices P that is commonly adopted in financial econometrics literature. Okay, that is the equation. as we know, log of price minus price in the earlier period equals alpha plus ut, when alpha mean and this is the constant are unknown parameters. Use the transformation of variable technique to show the conditional distribution of price, which is a log normal distribution. We're just simply taking we're just simply transforming this equation 1 by root over twice by sigma square price exponential of log of pt minus the lagged price, log of price minus lagged price minus the constant alpha goes to the right hand to the left hand side, where mu remains in the right hand side. Okay, we probably have idea on the u is the residual. It's not mu, I'm sorry, u is the residual because mean is 0, variance is sigma square for the residual. Okay, it's just for the residual, however it's the residual u. Okay, for a sample size of t to sigma square, construct the log likelihood function and derive alpha and sigma square, mu mean and sigma square based on conditional distribution. Use the results to compute theta hat for 3 stock indexes. Estimate asset price distribution for each index using maximum likelihood. So basically I'm constructing the distribution, then I'm computing the parameter theta with maximum likelihood, then I'm making the estimates, and then I'm also estimating return. And then I'm actually estimating again in terms of R. I don't need to do it many times, but yeah. So load asset prices, price Australia divided by 1000. I'm normalizing it, just normalizing it. Then y equals, there's no function here, y equals trimmer. Okay, this is interesting. Always remember, because I'm talking about time differences, lagged values. Trimmer function, basically what does that mean? Trimmer means log of, I'm taking pt price matrix, I'm taking the log of the price matrix, and from the price matrix I'm trimming all the first element. So starting from the second element, I'm trimming nothing from the last element, minus I'm trimming nothing from the first element and one row from the last element. So it gives you kind of like step by step. So the first one is this, the second one is this. So basically these two differences are important when we are talking about returns, when we are transitions, when we are talking about transitions from log price at t minus 1 to log price at t. It is a common method, always remember that. How we are doing the transformation in R, just for pt minus 1 is I'm removing the first element, first row in the first bracket, minus pt length of pt, I'm removing the last, and it's quite easy. Minus pt minus length of pt, not minus pt, price minus 1 in the third bracket, that's the trick. And last one is in the third bracket minus, not minus 1 but minus price itself, length of pt in the last. So that's all. Alpha mean of y, mean of y, mean of y minus alpha whole square minus element by element mean. Here I think R takes everything by element, I don't need to like mention anything. So that's all. This was quite simple. There is another model called the Vance model, but I'm not sure I'll go into that because I need to understand, read and understand Vance model, maybe in later videos if necessary. Thank you.